The ocean feels like home. We vacation on it, sail across it, swim in it, fish from it, and casually dump rubber ducks into it to see where they end up. It laps against our cities, shapes our climate, and fills most of the view when astronauts look back at Earth. And yet, beneath that friendly blue surface is a world so unknown that it might as well come with its own alien language and a warning label that says, "Here be things with too many teeth." That strange contradiction is where our story begins. Because while we talk about exploring space as humanity's greatest adventure, the uncomfortable truth is that we have a better understanding of the surface of Mars than we do of the ground beneath our own oceans. Apparently, it is easier to map a planet millions of miles away than the one we are currently standing on, which feels like misplacing your keys while holding them. If this gentle look at why so much of the ocean remains unmapped and unexplored helps you relax tonight, please like the video, subscribe to the Deep Sea Documentary channel, and leave a comment sharing when and where you're listening, so this calm science can reach more people who fall asleep to the deep sea's unknown. This is not just a fun fact meant to make you question our life choices. Scientists really do have detailed maps of Mars, complete with mountains, valleys, and ancient riverbeds. We can point to specific rocks on the Martian surface and say, with confidence, yes, that one looks suspiciously like it was shaped by water billions of years ago. Meanwhile, here on Earth, vast stretches of the ocean floor are still represented by vague blobs and educated guesses. And it is like having a high-definition portrait of your neighbour's living room, but only a blurry silhouette of your own basement. And that basement, statistically speaking, is probably where all the interesting stuff is hiding. Part of the reason the ocean feels familiar is because we mostly interact with its surface. Sunlight sparkles, waves roll in, boats float, and everything seems calm and understandable. This creates an illusion of knowledge. We assume that because we can see the top, we somehow understand the whole thing. It is the same logic as assuming you know a person's entire personality because you saw them smile once at a grocery store. The deep ocean, however, begins just beyond where light can easily reach, and from there on down, it becomes a place that actively resists our curiosity. It does not announce its secrets, and it does not want to be casually observed. It is polite at the surface and deeply uncooperative underneath. What makes this even stranger is that humans are, by nature, explorers. We crossed continents, climbed mountains, and launched ourselves into space, strapped to towers of controlled explosions. We put footprints on the moon using computers less powerful than a modern toaster. And yet, when it comes to the ocean, we mostly stop at the shoreline and say, "Yep, that is wet, seems deep, moving on." The result is that the ocean has become both a symbol of life and a reminder of how little we truly know about our own planet. It feeds us, regulates our climate, and produces much of the oxygen we breathe, all while quietly keeping its lower half shrouded in mystery like a cosmic introvert. See, there is also a psychological aspect to this unfamiliarity. Space feels distant, but clean, empty. The ocean feels close, but crowded with unknowns. When people imagine Mars, they think of dusty plains and silent horizons. When they imagine the deep sea, they picture darkness filled with lurking shapes and glowing eyes. One feels lonely, the other feels watched. That difference matters, because fear has a way of slowing curiosity. We romanticize space exploration as bold and heroic, while deep-sea exploration often feels like poking a very large, very patient beast with expensive equipment and hoping it does not swallow it whole. And yet, the irony is that the ocean is not some distant realm. It is Earth's largest environment. It is the background system that makes everything else work. the water cycle, weather patterns, food chains, and even the air itself are deeply tied to what happens in those unseen depths. The ocean floor records Earth's geological history like a slowly moving archive, preserving clues about shifting continents and ancient climates. Ignoring it would be like trying to understand human history by only reading the last page of the book. So when we say the ocean feels familiar yet alien, we are really admitting something about ourselves. We are comfortable with what we can easily see, and strangely indifferent to what lies just out of reach. The ocean challenges that comfort. It sits right there, covering most of the planet, quietly reminding us that exploration does not always mean looking up. Sometimes it means looking down, past the glittering surface, into a world that is still waiting for us to ask better questions. And to understand why so much of the ocean remains unmapped, you first have to grasp just how outrageously large it is. Not large in a poetic sense. Not large like, wow, that is a big lake. But large in a way that actively breaks the human brain's ability to visualize it. The ocean covers more than 2/3 of Earth's surface, wrapping around continents like an oversized blanket that someone forgot to fold. If Earth were shrunk down to the size of a basketball, the land would be little more than scuffed patches, while the ocean would dominate nearly every inch you touched. Mapping something that vast is not just a technical challenge. It is a logistical marathon where the finish line keeps moving. When we imagine mapping, we tend to picture a satellite snapping neat pictures from above, stitching them together into a tidy global map. And that works wonderfully for land, because continents politely sit still and allow themselves to be photographed. The ocean does not offer that courtesy. From above, all you see is a moving surface of waves, reflections, clouds, and storms. The actual terrain we care about lies kilometers below, hidden beneath a constantly shifting layer of water that refuses to stay quiet long enough for a proper look. It is like trying to sketch the layout of a city by staring at its reflection in a shaken mirror. The scale problem becomes even more absurd when you consider depth. The ocean is not a flat puddle. It is a three-dimensional world with slopes, plains, ridges, trenches, and features that dwarf anything found on land. Some underwater mountain ranges stretch longer than entire continents, while deep trenches plunge so far down that stacking Mount Everest inside them would still leave room to spare. Mapping this is not just about covering area. It is about capturing vertical complexity across a space so large that even small sections can take years to study. Every expedition that maps a tiny patch of seafloor is like placing a single puzzle piece into a box meant to hold millions, without a picture on the lid. This is where the blindfolded mountain analogy comes in. Imagine being dropped into an enormous mountain range with a blindfold on. You are allowed to feel the ground directly beneath your feet, but only one step at a time. You cannot climb too fast. You cannot see ahead, and you are carrying equipment that is expensive, delicate, and allergic to mistakes. Now imagine that the mountain range covers most of the planet. That is what ocean mapping feels like. Progress is slow, methodical, and deeply humbling. Each small success highlights how much remains untouched. The size of the ocean also means that even defining what mapped means becomes tricky. Mapping is not a single achievement you unlock like a badge. There are levels of detail, from broad outlines to fine-scale textures. Creating a rough global picture is one thing. Understanding the fine features that matter for geology, biology, and climate is something else entirely. As the ocean expands in all directions, so does the amount of information required to truly know it. The bigger the area, the more resolution matters, and the more time it takes to collect it. It is the difference between knowing that a forest exists and knowing where every tree stands. There is also the problem of prioritization. When something is this large, you cannot map it all at once. Choices must be made about where to focus, which means vast regions wait their turn, sometimes for decades. Entire swaths of the ocean floor remain unexamined, simply because there has never been a compelling reason to visit that exact spot before. Not because it is unimportant, but because everything else is also important. And there are only so many ships, tools, and human hours to go around. The ocean's size forces exploration to be selective, and selectivity leaves gaps. What makes this even more challenging is that the ocean does not present obvious boundaries. On land, maps are divided by borders, coastlines, and visible landmarks. Underwater, those cues vanish. One patch of seafloor blends seamlessly into the next, stretching on without clear signs of transition. It is easy to underestimate how much ground has been covered, or how much remains, because there is no obvious sense of progress. The ocean does not reward you with a view from the summit. It just keeps going. So when people ask why the ocean is still so poorly mapped, the simplest answer is also the most daunting. It is because the ocean is enormous in a way that resists human scale. It does not fit neatly into our timelines or our expectations of exploration. Every attempt to chart it reveals not just new features, but new reminders of how small our efforts are compared to the task. And that, perhaps, is the ocean's greatest trick. It does not hide because it is sneaky. It hides because it is vast, and we are trying to understand it one careful step at a time. And as you descend into the ocean, nothing dramatic happens at first. The water stays clear, fish drift by, and everything feels calm, almost welcoming. But depth is a patient villain. It does not jump out at you with flashing lights or ominous music. Instead, it quietly adds weight. Every meter downward stacks more water above you, and water, it turns out, is far heavier than it looks when it is not busy sparkling in the sun. By the time you reach the deep sea, that innocent blue liquid has transformed into a colossal invisible fist, pressing down from all directions at once. Pressure in the ocean increases steadily with depth, and unlike many dangers, it cannot be dodged or outrun. It is everywhere, squeezing equally from the sides, above and below. At great depths, this pressure becomes so intense that it fundamentally changes the rules of engineering. Materials that behave perfectly fine on land suddenly become fragile. Tiny imperfections turn into catastrophic failures. A solid metal structure can buckle inward without warning, collapsing in milliseconds like it was made of foil. The ocean does not crush things violently. It crushes them decisively, like a hydraulic press that never gets tired and never loosens its grip. For exploration, this pressure is a nightmare. Every camera, sensor, and vehicle sent into the deep must be built like a miniature fortress, designed to survive forces that would easily destroy everyday objects. Even a small leak is disastrous. Water does not politely drip in under pressure. It explodes inward, instantly flooding compartments and destroying electronics. The deep sea is brutally efficient at finding weaknesses. It is like an exam where the ocean is the examiner, and it marks your mistakes with immediate, total failure. This creates a fundamental problem for mapping and exploration. To withstand extreme pressure, equipment must be thick, reinforced, and often spherical in shape, because spheres distribute pressure evenly. But adding strength adds weight, and weight creates its own challenges. Heavy equipment is harder to deploy, harder to maneuver, and far more expensive to recover if something goes wrong. Every additional layer of protection is a trade-off. Build it too light, and it implodes. Build it too heavy, and it becomes impractical to use. Engineers walk a narrow line between survival and usability, while the ocean waits patiently below, unconcerned with human design dilemmas. The pressure also limits how long missions can last. Even if a vehicle survives the descent, the constant stress takes a toll over time. Repeated exposure can weaken materials in subtle ways, causing fatigue that is difficult to predict. A vessel that performs flawlessly on one dive might fail on the next, not because anything obvious changed, but because the pressure quietly accumulated damage behind the scenes. This unpredictability makes deep-sea missions feel like high-stakes gambling, except the house always has several kilometers of water on its side. Human presence makes things even more complicated. Sending people into the deep requires not only protecting equipment, but also maintaining a livable environment inside the vehicle. The pressure outside wants to turn the interior into a very small, very flat space. Keeping it at normal atmospheric conditions demands thick walls, precise seals, and constant monitoring. Every human dive is therefore rare, costly, and carefully planned, which severely limits how much of the ocean can be directly observed. Most of the deep sea remains unseen by human eyes, not because we lack curiosity, but because our bodies are hilariously unsuited for that environment. The soda can analogy exists for a reason. A soda can looks sturdy until external pressure overwhelms its thin walls, at which point it collapses instantly. In the deep ocean, the same principle applies, just scaled up to a level that feels almost unfair. Even strong materials can fail if the pressure difference becomes too great. This reality forces exploration to rely on machines that can survive where humans cannot. And even those machines operate under constant threat of being turned into expensive underwater confetti. Pressure also affects how we collect data. Instruments must function reliably while being squeezed by forces strong enough to alter their shape. Sensors can deform, measurements can drift, and components can behave differently under stress. Designing tools that not only survive pressure, but also remain accurate, is an enormous challenge. It is not enough for something to exist at depth. It has to work correctly, consistently, and predictably, all while being crushed by the weight of an ocean. In the end, pressure is one of the ocean's most effective gatekeepers. It does not block exploration outright. It simply raises the cost, complexity, and risk of every attempt. The deeper we go, the more the ocean reminds us that it is not just water. It is a force, slowly pressing down, testing every bolt and seal, and making sure that only the most carefully designed explorers are allowed to pass. At a certain point in the ocean, the sun simply gives up. It does not fade out dramatically or announce its departure. It just stops showing up. As you descend, the bright blues soften into darker shades, then into a dusky twilight, and finally into a darkness so complete it feels less like night and more like the absence of existence. This is the realm where sunlight no longer reaches, a vast volume of water permanently cut off from the star that powers nearly all life on Earth. It is here that the ocean earns its reputation as a planet-sized blackout room, and it is here that exploration becomes dramatically more complicated. Yet our cameras, which are the backbone of human observation, are fundamentally light-hungry devices. They do not see things on their own. They capture light that already exists. In the deep ocean, that light is gone. There is no ambient glow, no reflected shimmer, no helpful moonlight filtering down. A camera lowered into this darkness sees nothing at all unless it brings its own illumination. And bringing light into the deep sea introduces a cascade of new problems, each one more inconvenient than the last. Artificial lights must be powerful enough to pierce the darkness, but powerful lights consume energy, generate heat, and add bulk. They also create sharp contrasts, illuminating a small area while leaving everything else swallowed by blackness. This means that cameras often capture scenes that feel strangely claustrophobic, with bright foregrounds, fading abruptly into void. Mapping an environment like this is similar to trying to understand a cathedral. By examining it with a flashlight while standing in a pitch-black field, you might see incredible details, but you have no sense of the larger space they belong to. Darkness also distorts perception. Without natural light gradients, it becomes harder to judge distance, size, and shape. Objects can appear closer or farther than they really are. Surfaces can look smooth until light reveals unexpected textures, or rough until a different angle shows otherwise. For mapping, this uncertainty matters. Accurate visual interpretation relies on consistent lighting, and the deep sea offers none. Every image becomes a carefully staged moment rather than a natural snapshot, shaped by where the lights are placed and how they interact with particles in the water. Those particles are another problem. The ocean is not empty space. Even in its clearest regions, tiny bits of organic matter drift through the water. When strong lights hit these particles, they scatter the light back toward the camera, creating a snowstorm effect known to anyone who has ever tried to take a photo in fog or heavy snowfall. Instead of revealing the seafloor, the lights can turn the water itself into a glittering curtain that hides what lies beyond. The deeper you go, the worse this effect can become, turning visibility into a constant negotiation rather than a guarantee. Darkness also limits human intuition. On land, we rely heavily on visual cues to orient ourselves. Shadows, horizons, airs, and landmarks help us understand where we are and how things are arranged. In the deep ocean, there is no horizon, no sky, and no up or down that feels intuitive. Everything exists in a floating black space where orientation must be determined by instruments rather than instinct. This makes exploration mentally demanding and increases the chance of misinterpretation. When your eyes cannot be trusted, every decision becomes slower and more deliberate. From a storytelling perspective, darkness is dramatic. From a scientific perspective, it is exhausting. Each moment of observation must be planned, lit, recorded, and interpreted with care. There is no casual glancing around. Every second of footage is the result of deliberate effort. This slows down exploration and makes comprehensive mapping incredibly time-consuming. You cannot simply sweep your gaze across the landscape. You must reveal it piece by piece, like uncovering a mural in a room with no windows and a single lamp. Darkness also shapes the unknown in powerful ways. When people imagine unexplored places, they often imagine darkness first. The lack of light invites imagination to fill in the gaps, sometimes with exaggerated fears or expectations. This psychological effect influences how exploration is perceived and prioritized. Dark places feel more intimidating, more alien, and harder to justify exploring, even when they hold immense scientific value. The ocean's darkness, therefore, is not just a physical barrier, it is a mental one. In the end, the absence of sunlight transforms the deep ocean into a place where seeing is never simple and never free. Every image is earned, and every visual clue is incomplete. The darkness does not hide the seafloor out of malice. It hides it by default, quietly enforcing the rule that knowledge here must be extracted, not observed casually. In a world without light, understanding becomes slower, harder, and far more precious. If pressure is the ocean's brute force and darkness its cloak, then cold and corrosion are its slow, methodical assassins. They do not crush or blind. They wait. Far below the surface, temperatures hover just above freezing, creating an environment that feels less like a place and more like a long-term endurance test for anything built by humans. Add salt to the mix, and the ocean becomes a master of quiet destruction, breaking down even the toughest machines one microscopic bite at a time. Deep-sea cold is not dramatic. There are no icy winds or swirling snowflakes. Instead, there is a constant bone-deep chill that never changes, never relents, and never gives equipment a chance to recover. Electronics, which are perfectly happy in climate-controlled labs, behave very differently in this environment. Cold slows chemical reactions inside batteries, reducing their efficiency and shortening mission durations. Lubricants thicken, making moving parts stiff and unreliable. Materials that flex easily at warmer temperatures can become brittle, increasing the risk of cracking under stress. The ocean does not need to snap equipment in half. It just needs to make it slightly less reliable, slightly more fragile, until something eventually fails. Then there is salt water, the ocean's most deceptively powerful ingredient. Salt is excellent at conducting electricity, which is fantastic if you are seasoning food, and terrible if you are protecting sensitive electronics. Even the smallest breach in a protective casing can allow salt water to creep in, setting off corrosion that spreads invisibly through circuits and connectors. Unlike dramatic failures, corrosion works quietly. A device may appear to function normally while its internal components are slowly being eaten away. By the time the problem becomes obvious, the damage is often irreversible. This combination of cold and corrosion makes the deep sea uniquely hostile to long-term exploration. Equipment left underwater for extended periods faces a constant assault. Metals oxidize, seals degrade, and protective coatings wear thin. As engineers must design systems that not only survive initial deployment, but continue to function after months or years of exposure. This is not a small challenge. It is an ongoing arms race between human ingenuity and chemistry has had billions of years to practice. Maintenance, which is routine on land, becomes a logistical nightmare in the deep ocean. You cannot simply send a technician down to tighten a bolt or replace a worn cable. Every repair requires retrieval, specialized facilities, and significant expense. As a result, equipment must be built to endure long stretches without human intervention. This necessity drives up complexity and cost, limiting how much gear can be deployed at once. The ocean's cold and salt do not just damage machines. They indirectly limit exploration by making everything more fragile, more expensive, and harder to replace. Cold also affects how materials age. Repeated exposure to near-freezing temperatures can cause microscopic changes in structure, especially in polymers and composites. These changes accumulate slowly, weakening components in ways that are difficult to predict. A seal that looks intact may suddenly fail. A cable that appears sound may snap under minimal strain. This unpredictability forces conservative design choices, which often means heavier, bulkier equipment. And heavier equipment is harder to deploy widely, narrowing the scope of exploration. Even data collection suffers. Sensors calibrated in warmer conditions may drift in accuracy when exposed to extreme cold. Chemical reactions used in certain instruments slow down, altering response times. To compensate, scientists must carefully account for temperature effects, adding layers of complexity to both design and analysis. The cold does not prevent measurement outright. It simply ensures that nothing works exactly the way it does on land. What makes this especially frustrating is how unremarkable the destruction looks from the outside. A piece of equipment may return from the deep ocean looking mostly fine, only to fail weeks later as corrosion continues its work. This delayed damage complicates planning and budgeting. Missions that appear successful on the surface may carry hidden costs that emerge long after the ship has returned to port. The ocean's patience becomes expensive. And yet, despite all of this, exploration continues. Engineers develop new alloys, improved coatings, and smarter designs to resist corrosion and function in the cold. Each advancement pushes the boundary a little further. But progress is incremental, and the environment never stops applying pressure, cold, and salt in perfect coordination. The ocean does not need to rush. It knows time is on its side. In the end, extreme cold and corrosion are reminders that the deep sea is not an event to be conquered, but a condition to be endured. It wears down our machines, not through drama, but through persistence. Like a very patient oceanic termite, it gnaws away at our technology, forcing us to respect the environment we are trying to understand. When vision fails in the ocean, sound steps in as the next best thing. Sonar is the workhorse of seafloor mapping, the method humans rely on to see through water by listening instead of looking. While the idea sounds simple enough, send out a sound wave, wait for it to bounce back, measure how long it took, and use that delay to calculate distance. In practice, this process is less like taking a clean photograph and more like trying to understand a room by shouting once and interpreting the echo while someone rearranges the furniture. Sound behaves in water in ways that are both helpful and deeply inconvenient. It travels far, which is why whales can communicate across entire ocean basins. But it also spreads, bends, scatters, and weakens as it goes. When a sonar pulse is emitted, it does not move like a laser beam. It fans out, interacting with layers of water, suspended particles, and uneven terrain. By the time it reaches the seafloor and returns, the signal has been altered in subtle but important ways. Now, the result is not a crisp outline, but an interpretation, a translation from echo into estimate. One of the core challenges is resolution. Sonar systems face a trade-off between coverage and detail. Low-frequency sound waves can travel long distances and map large areas quickly, but they produce coarse results, smoothing out fine features. High-frequency waves provide sharper detail but fade quickly, limiting how much area can be covered at once. This forces scientists to choose between seeing a lot of the ocean floor vaguely or seeing a small portion very clearly. Trying to do both at the same time is like wanting a wide-angle panorama and a microscopic close-up in a single snapshot. The seafloor itself complicates matters further. It is not a uniform surface that reflects sound evenly. Different materials absorb and scatter sound differently. Soft sediments, hard rock, steep slopes, and jagged formations all interact with sonar in unique ways. Some features reflect sound cleanly back to the receiver, while others deflect it away, creating shadows or gaps in the data. These blind spots are not empty spaces. They are simply areas where the sound did not return in a usable way. On a map, They appear as smudges, streaks, or missing patches, contributing to that fingerprint-like appearance. Angle matters too. If a sound wave strikes the seafloor at a shallow angle, it may skim across the surface rather than bouncing straight back. This can stretch or distort features, making slopes look gentler or sharper than they really are. Interpreting these distortions requires careful processing and a fair amount of educated guesswork. Sonar maps are not raw photographs. They are models built from indirect measurements, refined through algorithms that attempt to correct for known sources of error. Then there is noise. The ocean is not quiet. Natural sounds from waves, marine life, and geological activity mix with human-generated noise from ships and machinery. All of this background sound can interfere with sonar signals, reducing clarity. Separating meaningful echoes from irrelevant noise is a constant challenge. It is less like listening for a single voice in a silent room and more like trying to follow a whisper at a crowded party where everyone is also underwater. Even when the data is collected successfully, interpretation is not straightforward. Sonar returns intensity values, not labels. A bright spot on a map indicates strong reflection, not necessarily a specific feature. Is it a rocky outcrop, a steep slope, or simply a favourable angle? Determining that requires experience, additional data, and often follow-up surveys. This is why early sonar maps often led to revisions. What once looked like smooth plains later revealed complex structures when examined with improved techniques. The fingerprint analogy fits because sonar maps capture patterns rather than precise images. Like fingerprints, they are unique, textured, and informative, but not instantly readable. They require context to make sense. Two scientists can look at the same sonar map and emphasize different features based on their goals. One might focus on geological structures, another on potential habitats, another on navigational hazards. The map is a starting point, not a final answer. And technological improvements continue to sharpen these fingerprints, but they do not eliminate the underlying limitations. Sound will always behave like sound. It will always spread, scatter, and interact unpredictably with complex surfaces. Sonar mapping is therefore an exercise in approximation, building the best possible picture from incomplete information. It is powerful, indispensable, and imperfect all at once. In the end, sonar does not fail to map the ocean floor. It reveals it in a language that must be carefully translated. The blurry fingerprint it produces is not a flaw so much as a reminder of the medium we are working in. The ocean does not give up its shape easily, and even our best tools must listen carefully, interpret cautiously, and accept that some details will remain just out of reach. Yet, if curiosity were the only currency required to explore the deep ocean, we would have mapped it decades ago. Unfortunately, the ocean does not accept wonder as payment. It demands ships, fuel, crews, equipment, planning, insurance, and a small mountain of paperwork, all of which add up to a price tag that can make even well-funded research programs flinch. Deep-sea exploration is not just scientifically challenging. It is financially intimidating in a way that quietly determines how much of the ocean we get to know. At the center of this cost is the research vessel. These are not ordinary ships. They are floating laboratories packed with specialized gear, cranes, winches, navigation systems, and communication arrays. Operating one requires a trained crew that includes sailors, engineers, technicians, and scientists, all working around the clock. Keeping such a vessel at sea can cost tens of thousands of dollars per day, sometimes more. Every hour matters. Every delay burns fuel and money, and the ocean is not known for sticking to schedules. Fuel alone is a massive expense. Deep-sea missions often take place far from shore, requiring long transits across open water before any research even begins. Once on site, the ship must maintain precise positioning, sometimes for days, to deploy and recover equipment. Holding a large vessel steady in the open ocean is not trivial. Engines run constantly, consuming fuel at a rate that makes your car's gas mileage feel adorably insignificant. And unlike space missions, which travel through vacuum, ocean exploration drags its way through a dense, resistant medium that never stops pushing back. Then there is the equipment. Deep-sea tools are custom-built, highly specialized, and produced in small numbers. There is no mass market for submersible components or deep ocean sensors, which means there are no economies of scale. Each piece is expensive because it has to be. Add redundancy, backups, and spares, and the budget grows quickly. Losing a single piece of equipment to a malfunction or accident can wipe out a significant portion of a mission's funding. The ocean is not gentle with mistakes, and mistakes are costly. Human expertise adds another layer. Deep-sea exploration relies on highly trained specialists who understand complex systems and can respond to unexpected problems in real time. These skills take years to develop and are in high demand. Paying for that expertise is essential, because a small error in planning or execution can turn a multi-million-dollar mission into a very expensive lesson in what not to do. Unlike some other scientific fields, there is little room for improvisation once you are at sea. Time is perhaps the most underestimated cost. Planning a deep-sea expedition can take years. Permits, logistics, equipment testing, and crew coordination must all align. Weather windows are narrow, and missed opportunities can mean waiting an entire season to try again. During that waiting period, funding must still be secured, teams retained, and equipment maintained. The clock keeps ticking, even when the ship is docked. Comparisons to space exploration often come up, and while both are expensive, space benefits from clear narratives and long-term investment. Space missions are seen as iconic, forward-looking endeavors. Deep-sea exploration, by contrast, often struggles for attention. Its results are less immediately visible to the public, and its risks feel less glamorous. As a result, funding is more fragmented and uncertain. Researchers must constantly justify why studying the ocean floor is worth the expense, even though it plays a critical role in understanding our planet. The irony is that space missions often involve a single launch and years of data collection, while deep-sea exploration requires repeated trips, each with its own costs. The ocean does not stay still long enough for a one-time visit to suffice. Conditions change, equipment wears down, and new questions arise. Exploration becomes a recurring investment, rather than a one-off event. All of this means that choices must be made. While limited budgets force scientists to focus on specific goals, leaving many areas unexplored simply because there is not enough money to go around. It is not a lack of interest that leaves gaps on the map. It is arithmetic. In the end, the staggering cost of deep-sea exploration acts as a powerful filter. Only the most compelling questions, the strongest proposals, and the most carefully planned missions make it to sea. The ocean remains vast and unknown, not because we are unwilling to explore it, but because every attempt comes with a bill that reminds us just how expensive curiosity can be. On land, navigation is effortless to the point of being boring. A phone buzzes, a voice calmly tells you to turn left, and you obey without questioning the miracle happening in your pocket. Underwater, that miracle stops working almost immediately. GPS signals, which rely on radio waves from satellites, cannot penetrate water to any useful depth. The moment a vessel submerges, it is effectively cut off from the global positioning system, left to navigate the ocean the old-fashioned way, by inference, estimation, and a healthy dose of caution. Exploring the deep sea without GPS is less like following a map and more like driving blindfolded while counting your steps and hoping nothing unexpected appears in front of you. Without direct positioning, underwater vehicles must rely on dead reckoning, a method that calculates current position based on a known starting point, speed, direction, and time traveled. In theory, this works well. In practice, small errors accumulate quickly. A slight miscalculation in speed or direction can compound over hours, turning a precise trajectory into a wandering guess. Ocean currents add another layer of uncertainty, subtly pushing vehicles off course in ways that are difficult to detect from within a sealed hull. By the time a mission ends, the actual path traveled may differ significantly from the planned one. To compensate, underwater navigation systems use a combination of sensors. Gyroscopes track orientation, accelerometers estimate movement, and pressure sensors provide depth information. Together, these systems create a picture of motion rather than position. They can tell a vehicle how it is moving, but not exactly where it is in the larger ocean. This distinction matters. Knowing that you travelled forward for 10 minutes does not tell you what you passed over or where you are relative to the seafloor features you want to study. Acoustic navigation helps fill some of these gaps, but it comes with its own limitations. Sound-based positioning systems require reference points, either on the seafloor or on the surface. These reference points must be carefully placed and calibrated, a process that takes time and resources. Even then, sound signals can be delayed, distorted, or blocked by terrain. Position estimates improve, but they are never instantaneous or perfectly precise. Every update arrives with uncertainty attached, like a weather forecast that says, probably sunny unless the ocean disagrees. This uncertainty affects how exploration is conducted. Missions must be planned conservatively, with slower movements and frequent checks to avoid collisions or missed targets. Mapping becomes a cautious exercise, prioritizing safety over speed. Vehicles cannot simply roam freely. They must move deliberately, constantly updating their best guess of where they are. This slows down data collection and limits how much territory can be covered in a single mission. The lack of precise navigation also complicates data interpretation. When a feature is detected, knowing its exact location is crucial for follow-up studies. If position estimates are off, revisiting the same spot becomes difficult. Scientists may know that something interesting exists somewhere in a broad area, but pinpointing it again can be frustratingly elusive. It is like trying to return to a specific tree in a forest after walking around blindfolded for an hour. Human-operated vehicles face additional challenges. Our pilots must interpret instrument readings while maintaining awareness of surroundings they cannot see clearly. Reaction times are slower, decisions more deliberate. Every movement is intentional because correcting mistakes is far harder underwater than on land or in the air. The blindfolded driver analogy fits because underwater navigation is an exercise in trust. Trusting instruments, calculations, and experience more than direct observation. Autonomous vehicles handle navigation differently, but they face the same fundamental limitations. They rely on algorithms that estimate position based on movement and occasional acoustic updates. When conditions change unexpectedly, these systems must adapt without human intuition. A small navigational error can send a vehicle off its intended path, potentially missing key areas, or ending up somewhere unplanned. Recovering from such errors is not always possible during a mission. All of this means that underwater navigation is never absolute. It is probabilistic, a best guess refined over time. This uncertainty shapes exploration strategies, forcing scientists to accept margins of error that would be unacceptable on land. The ocean does not offer signposts or clear coordinates. It demands patience and precision in equal measure. In the end, navigating the deep sea is about managing uncertainty rather than eliminating it. Submarines and underwater vehicles move carefully through a world where location is inferred rather than known. Each successful mission is a testament not to perfect navigation, but to the ability to operate effectively, despite never being entirely sure where you are. Before a single piece of equipment ever touches the deep sea, explorers must first survive the surface. This is an often overlooked irony of ocean exploration. The most advanced technology in the world can be rendered useless by a patch of bad weather and a few meters of unruly water. The ocean's surface is the gateway to its depths, and it is a gatekeeper with a famously unpredictable temperament. Storms, waves, and currents do not care about schedules, budgets, or months of planning. They arrive when they want, and when they do, missions stop. Waves are not just an inconvenience. For large research vessels, they can make precise operations impossible. Deploying equipment into the ocean requires stability. Whilst cranes must lower heavy instruments smoothly, cables must remain taut, and vehicles must enter the water at just the right angle. Even moderate waves can turn these delicate maneuvers into high-risk gambles. A sudden roll of the ship can swing equipment like a wrecking ball, threatening both the gear and the crew. When conditions deteriorate, the safest option is often to delay or cancel operations entirely. Storm systems amplify these problems. High winds whip up waves, reduce visibility, and create chaotic surface conditions. Rain and spray interfere with deck operations, making already complex tasks more dangerous. Lightning adds another layer of risk, forcing crews to halt work to avoid turning metal equipment into accidental conductors. In severe cases, ships must abandon research sites and seek shelter, losing valuable time and fuel in the process. The ocean does not negotiate, it simply enforces its terms. Currents complicate matters even on relatively calm days. Surface currents can push vessels off position, making it difficult to maintain the precise location needed for deep sea work. Holding station over a specific point on the seafloor is a constant struggle against moving water. If the ship drifts, cables can angle dangerously, vehicles can miss their targets, and data quality can suffer. Correcting for this requires continuous adjustments, burning fuel, and increasing wear on equipment. Weather forecasting helps, but it is not foolproof. Ocean conditions can change faster than predictions, especially in remote regions where data is sparse. A calm morning can give way to rough seas by afternoon, catching crews mid-operation. And decisions must be made quickly, balancing the desire to continue work against the risk of damage or injury. Caution often wins, because the cost of pushing too far can be catastrophic. These interruptions have cascading effects. A delayed deployment can throw off an entire mission schedule. Research vessels operate on tight timelines, with limited windows before they must return to port or move to the next assignment. Losing a day or two to weather can mean skipping planned dives or abandoning objectives altogether. Unlike land-based research, there is little flexibility to simply extend the timeline. The ship, the crew, and the funding all have limits. Surface conditions also affect recovery operations, which can be even more stressful than deployment. Retrieving equipment requires precision and timing, as a vehicle returning to the surface must be located, secured, and lifted aboard, all while the ship moves with the waves. Rough seas increase the risk of collisions between the vehicle and the hull, potentially damaging both. In extreme cases, recovery may be postponed, leaving expensive equipment bobbing in the open ocean, exposed to further hazards. For scientists, this unpredictability is a constant source of frustration. Months or years of preparation can hinge on a few days of favorable weather. Entire research questions may remain unanswered simply because the ocean refused to cooperate. It is a reminder that exploration is not just about technology and knowledge, but about negotiating with a dynamic, living system that operates on its own terms. The ocean's surface is where human plans meet natural reality. Yet it is a reminder that before we can explore the hidden depths, we must first earn safe passage through a restless boundary layer that never truly settles. Storms will come, waves will rise, and currents will shift, indifferent to our ambitions. The ocean does not check forecasts, and it certainly does not apologize for cancellations. Speed is something humans have grown very fond of. We stream movies instantly, cross continents in hours, and expect progress bars to move with reassuring urgency. The deep ocean, however, operates on a schedule that predates impatience by a few 100 million years. When it comes to mapping the seafloor, speed is not just limited, it is fundamentally incompatible with accuracy. Deep-sea mapping advances at a pace so slow that it makes glaciers look like they are in a hurry, turning exploration into a geological version of watching paint dry, except the paint is invisible and costs millions of dollars per hour. The slowness begins with proximity. To collect meaningful data, mapping instruments must stay relatively close to the seafloor. The closer they are, the better the detail, but closeness comes at the cost of coverage. A vehicle flying low above the bottom can only scan a narrow strip at a time. This means that even under ideal conditions, progress is measured in small, deliberate increments. Each pass covers a limited swath, and then the vehicle must turn around and do it again, slightly offset, like mowing an endless underwater lawn, with extreme precision and no visual feedback. Movement itself must be controlled and cautious, and sudden changes in speed or direction can compromise data quality or risk collisions with unseen terrain. As a result, mapping vehicles crawl rather than cruise. Inches per second may not sound impressive, but at depth, that pace is deliberate. It ensures stability, consistency, and safety. Unfortunately, it also means that mapping a single square kilometre can take hours or days, and mapping entire regions can stretch into years. There is also the issue of endurance. Deep sea mapping missions are constrained by power supply, data storage, and operational limits. Vehicles cannot run indefinitely. Each mission has a finite duration, after which the vehicle must be recovered, serviced, and prepared for another deployment. This stop-and-start rhythm fragments progress. Mapping is not a continuous sweep of the ocean floor. It is a series of careful, disconnected efforts stitched together over time. The human side of this slowness is equally significant. Scientists do not simply collect data and move on. They must monitor systems, adjust parameters, and respond to unexpected conditions. Every decision is made deliberately, because correcting errors later is difficult or impossible. This cautious approach further slows the process, but it is necessary. Rushing in the deep sea is a reliable way to lose equipment and data. Even when a mission goes perfectly, the sense of progress can be deceiving. A week at sea may produce detailed maps of a surprisingly small area. On a global scale, these achievements barely register. The ocean is so vast that even sustained mapping efforts feel like drops in a very deep bucket. This can be demoralizing, or especially when compared to the rapid progress seen in other scientific fields. But the comparison is unfair. Mapping the deep ocean is not a race. It is an accumulation. The slow pace also affects how exploration is perceived by the public. There are no dramatic breakthroughs every day, no sudden reveals of entire landscapes. Instead, progress comes as incremental improvements, subtle refinements, and gradually expanding patches of knowledge. This makes it harder to generate excitement and support, even though the work is essential. Watching paint dry is not thrilling, but it does eventually result in a finished wall. From a scientific perspective, slowness has an upside. It forces careful planning and thoughtful prioritization. Each mapped area is chosen for a reason, whether to answer a specific question or fill a critical gap. And this intentionality ensures that limited resources are used effectively. The ocean may not be mapped quickly, but it is mapped purposefully. The frustration of slow mapping is ultimately a reminder of scale and patience. The ocean was not shaped overnight, and understanding it will not happen quickly either. Each inch of seafloor mapped is a small victory, a piece of a puzzle so large it can only be assembled one careful move at a time. Progress may be slow, but it is steady, and in the deep ocean, steady is the only pace that works. One of the greatest paradoxes of deep-sea exploration is that the more we learn, the more careful we realize we must be. The deep ocean is not an empty wasteland waiting to be claimed or conquered. It is a living environment, often delicate, sometimes ancient, and frequently unfamiliar, in ways that challenge our assumptions about resilience. Every descent into the depths carries an ethical question alongside the scientific one. How do you study a place without harming it, especially when you do not yet understand how it works? Many deep-sea ecosystems exist under conditions that are remarkably stable. Temperatures barely change, disturbances are rare, and biological processes unfold at a slow, steady pace. In such environments, even small disruptions can have outsized consequences. A piece of equipment scraping the seafloor might damage organisms that took centuries to grow. Sediment clouds stirred up by a passing vehicle can smother nearby life or alter chemical balances in ways that persist long after the mission ends. The deep ocean remembers interference far longer than we do. Yet this fragility forces scientists to move with restraint. Exploration plans are designed to minimize contact, reduce disturbance, and avoid sensitive areas whenever possible. Vehicles are piloted carefully to prevent collisions. Sampling is limited and targeted rather than widespread. Even lighting choices are considered because intense illumination can stress or disorient organisms adapted to darkness. All of this caution slows exploration, but it is intentional. The goal is not just to observe the deep sea, but to leave it largely as it was found. Ethical concerns are amplified by the fact that many deep-sea habitats are still unknown. Scientists often do not realize an area is ecologically significant until they are already there. Entire communities can exist around features that were previously unmapped or misunderstood. As discovering such a habitat mid-mission creates a dilemma. Do you proceed with the original plan, or do you stop and reassess to avoid potential harm? Increasingly, the answer is to pause, observe, and rethink, even if it means sacrificing data or time. There is also a growing awareness that exploration itself can influence future activity. Maps and discoveries can attract interest beyond science, including commercial and industrial attention. Knowing this, researchers feel a responsibility to document ecosystems in ways that inform protection rather than exploitation. This adds another layer of care to how data is collected and shared. Exploration is no longer just about finding what is there. It is about considering what might happen next. Ethics also extend to sampling. While removing organisms or materials from the deep sea is sometimes necessary for study, but it is never taken lightly. Samples are finite, and regeneration can be extremely slow. Scientists must weigh the value of the knowledge gained against the impact of removal. This often leads to smaller sample sizes, fewer physical interactions, and a greater reliance on observation rather than extraction. The result is slower, but more responsible progress. This careful approach contrasts sharply with historical exploration narratives that celebrate boldness and speed. In the deep sea, barging in is not bravery, it is recklessness. The environment does not recover quickly from mistakes, and there is no easy way to undo damage once it is done. Ethical exploration requires humility, the recognition that curiosity does not grant ownership or entitlement. There is also an emotional dimension to this restraint. Scientists often describe a sense of awe when encountering untouched deep-sea habitats. That awe carries with it a desire to protect rather than disturb. Slowing down becomes not just a technical necessity, but a moral choice. The deep ocean is one of the last places on Earth where human presence is rare, and preserving that rarity has value in itself. Ultimately, ethical considerations act as a brake on exploration, but they also give it meaning. By choosing care over speed, scientists acknowledge that discovery comes with responsibility. The slow pace is the cost of respect. In the deep sea, learning to move gently is not a limitation. It is part of what it means to truly explore. The ocean may look borderless from the surface, but politically, it is anything but. Beneath the waves lies a complex web of national claims, international agreements, and legal definitions that divide the seafloor into zones of responsibility and control. For scientists, this invisible grid can be as challenging to navigate as the physical environment itself. Exploring the deep ocean is not just a matter of engineering and curiosity. It is also an exercise in diplomacy, compliance, and paperwork that would make even the most patient bureaucrat sigh. Countries exert rights over large portions of the ocean through defined maritime zones. These zones grant nations authority over resources, research activities, and environmental management within their boundaries. While the intent is to create order and protect interests, the practical effect on exploration is often delay and complication. Before a single instrument is deployed, researchers must determine who has jurisdiction over the area, what permissions are required, and which regulations apply. This process can take months or years, long before any data is collected. Permits are not standardized. Each country has its own rules governing scientific research, equipment use, sample collection, and data sharing. What is allowed in one region may be restricted or prohibited in another. Scientists must adapt their plans accordingly, sometimes redesigning entire missions to meet specific legal requirements. This administrative work is essential, but it slows progress and consumes resources that could otherwise be spent on exploration itself. The complexity increases when research areas lie near boundaries or span multiple jurisdictions, as a single expedition might cross through several zones, each with different regulations. Coordinating compliance across these borders requires careful planning and often multiple approvals. A mission that looks straightforward on a map can become a legal puzzle once political lines are taken into account. The ocean floor may be continuous, but governance is not. International waters present a different set of challenges. Areas beyond national jurisdiction are governed by international agreements designed to balance access, conservation, and shared benefit. While these frameworks aim to encourage cooperation, they also introduce additional layers of oversight. Proposals must align with international norms, and data may need to be shared in specific ways. Negotiating these requirements takes time and expertise, adding to the overall complexity of exploration. Political considerations can also influence which areas receive attention. Regions with clear, cooperative governance structures are often easier to study, while politically sensitive areas may remain unexplored despite scientific interest. This creates uneven coverage, not because of environmental difficulty, but because of human boundaries. Entire sections of the ocean floor can remain blank on maps, simply because the paperwork is daunting. There is also the issue of trust. Some nations are cautious about allowing foreign researchers to operate in their waters, concerned about resource exploitation or security. Building trust requires transparency, collaboration, and often long-term partnerships. While these relationships can be incredibly valuable, they take time to establish. Exploration moves at the speed of diplomacy rather than curiosity. For scientists, navigating this political landscape becomes part of the job. Teams often include legal advisors and policy experts alongside engineers and biologists. Research proposals must address not only scientific goals, but also compliance, benefit sharing, and environmental safeguards. The result is a more holistic approach to exploration, but also a slower one. Despite these challenges, political frameworks are not inherently obstacles. They reflect the reality that the ocean is shared, and that exploration must consider national and global interests. When managed well, international cooperation can enable large-scale projects that no single country could undertake alone. The difficulty lies in aligning priorities, timelines, and expectations across diverse stakeholders. In the end, political borders turn the seafloor into more than a physical landscape. They make it a legal and diplomatic one. Exploration becomes a journey through regulations as much as through water. Progress depends not only on technology and courage, but on patience, negotiation, and the willingness to navigate an underwater paperwork maze where the slowest currents are made of rules. Hidden within the world's most secure vaults and encrypted servers are ocean maps that most scientists will never see. These are not rough sketches or speculative models, but highly detailed representations of the seafloor, created not for curiosity or discovery, but for strategy and defense. And while much of the ocean remains officially unmapped, the uncomfortable truth is that some of its most precise charts already exist. They are simply classified, protected by military secrecy, rather than shared in the spirit of science. Naval forces have strong reasons to care deeply about the shape of the seafloor. Underwater terrain influences how sound travels, how vessels move, and how effectively equipment can operate. Knowing where slopes, ridges, and valleys lie can provide tactical advantages that are not obvious from the surface. As a result, militaries have invested heavily in mapping certain regions of the ocean with remarkable precision. These efforts, driven by security concerns, often outpace civilian scientific programs in both funding and technical capability. The data collected during these operations is incredibly valuable, but it is also sensitive. Revealing detailed maps could expose strategic routes, operational patterns, or vulnerabilities. Once such information is released, it cannot be taken back. For military planners, secrecy is not optional. It is a core requirement. This means that even when data could significantly advance scientific understanding, it remains inaccessible, locked behind classification barriers that prioritize national security over open knowledge. This creates a strange disconnect. Scientists working to understand the ocean may struggle with incomplete or coarse maps, unaware that far more detailed information exists just beyond their reach. From the outside, it looks like a technological limitation. From the inside, it is a policy decision. The ocean is not unmapped because no one has looked. It is unmapped because not everyone is allowed to see what has been found. The classification of ocean data also influences where scientific exploration happens. Civilian researchers tend to focus on areas where data is publicly available or where permissions are easier to obtain. Meanwhile, regions of strategic interest may be extensively mapped, but remain scientifically underexplored in the public domain. This skews our collective understanding, creating knowledge gaps that are political rather than environmental. There are occasional pathways for collaboration. In some cases, older or less sensitive data is declassified and released, benefiting both science and education. However, this process is slow and selective. Data may be outdated by the time it becomes public, or stripped of details deemed too revealing. While better than nothing, these releases rarely match the quality or completeness of what remains classified. The existence of hidden maps also raises philosophical questions about ownership of knowledge. The ocean is a shared global environment, yet information about it can be treated as a strategic asset. This tension reflects broader debates about transparency, security, and the role of science in society. Should knowledge about Earth's largest ecosystem be restricted, or is some level of secrecy unavoidable in a world where information can be weaponized? For scientists, this reality is both frustrating and motivating. It highlights the need for independent, open exploration efforts that generate publicly accessible data. And it also underscores the importance of advocating for data sharing policies that balance security with scientific progress. While not all information can or should be released, greater cooperation could dramatically accelerate our understanding of the ocean. Ultimately, military secrecy adds another layer to the mystery of the deep sea. It means that the map we see is not the map that exists. Somewhere, detailed charts of underwater landscapes lie in darkness, not because the ocean is hiding them, but because humans are. The challenge for the future is deciding how much of that hidden knowledge can be brought into the light without compromising the very security that created it. Collecting data from the deep ocean is only the beginning. Once the mission ends and the ship returns to port, the real work starts quietly. How far from rolling waves and dramatic descents. Hard drives are unloaded instead of anchors, and the challenge shifts from surviving the ocean to surviving the data. Deep sea mapping produces staggering amounts of information, and turning that raw flood into something meaningful can take years. In many ways, the computers tasked with this job work harder than the submarines that gathered the data in the first place. Modern mapping systems do not produce tidy images. They generate streams of numbers, timestamps, signal strengths, positions, and metadata, all layered together. Each pass over the seafloor adds more detail, but also more complexity. The sheer volume is overwhelming. A single expedition can produce terabytes of data, enough to fill libraries of storage with digital equivalents of scribbled notes waiting to be deciphered. But managing this information requires careful organization before analysis even begins. Cleaning the data is the first major hurdle. Raw data sets are messy. They contain errors, gaps, and artifacts introduced by equipment behavior, environmental conditions, or momentary glitches. Before scientists can trust what they see, they must identify and correct these issues. This involves filtering out noise, compensating for known distortions, and cross-checking measurements against reference points. It is meticulous work, performed step by step, often by teams of specialists. Rushing this stage risks building conclusions on flawed foundations. Once cleaned, the data must be integrated. Mapping does not rely on a single source of information. Multiple instruments often collect overlapping datasets, each with its own format and resolution. Combining these into a coherent model is like assembling a jigsaw puzzle where the pieces come from different manufacturers and do not quite agree on the picture. Aligning them requires sophisticated algorithms and a deep understanding of how each dataset was created. Small mismatches can lead to large errors if left unresolved. Computational demands escalate quickly. Processing high-resolution mapping data requires powerful hardware and efficient software. Even then, complex analyses can take days or weeks to run. When something goes wrong, which it often does, the process must start again. Computers churn through calculations, generating intermediate products that must be reviewed and validated. The phrase "making computers sweat" is not an exaggeration. Data processing pushes systems to their limits, and upgrades are a constant necessity. Human interpretation remains essential. Algorithms can identify patterns, but they cannot fully understand context. Scientists must examine results, question anomalies, and decide what features are meaningful. This interpretive step takes time and expertise. It also introduces discussion and debate, as different researchers may see different implications in the same data. Progress slows not because people are indecisive, but because careful interpretation is crucial to avoid misleading conclusions. The long timeline of data processing also means that results often lag far behind collection. A map published today may represent work done years earlier. During that time, methods improve, software evolves, and new questions emerge. Scientists must balance the desire to refine analyses with the need to share findings. Waiting too long risks irrelevance, but rushing risks inaccuracy. This tension shapes how quickly knowledge becomes available. Storage and preservation add another layer of complexity. Deep-sea data is valuable beyond its initial use. Future researchers may revisit old datasets with new tools or perspectives. Ensuring that data remains accessible, well-documented, and compatible with future systems requires ongoing effort. Without careful stewardship, information can become effectively lost, buried not under sediment, but under outdated formats and forgotten directories. All of this means that deep-sea mapping is not a single event, but a long process that extends far beyond the ocean itself. The slow pace of analysis is not a failure of technology, but a reflection of the richness of the information collected. Each dataset is a dense record of an environment we barely know, deserving of patience and attention. In the end, the challenge of data processing reminds us that exploration does not end when the vehicle surfaces. The ocean gives up its secrets reluctantly, and even when it does, understanding them takes time. The maps we see are the final products of years of invisible labor, where computers toil endlessly and scientists sift through digital mountains, turning raw echoes into knowledge. No matter how carefully a deep-sea mission is planned, there is one variable that refuses to stay predictable: life. The deep ocean is not empty, and its inhabitants do not read mission briefs. They drift, swarm, investigate, and occasionally interfere in ways that no engineer anticipated. For scientists, these biological surprises are equal parts delightful and disruptive. turning carefully choreographed expeditions into unscripted encounters with curious deep-sea celebrities who have a habit of standing directly in front of the camera. Many deep-sea animals are attracted to lights. In a world of perpetual darkness, a bright glow is an irresistible curiosity, like a porch light in summer. When exploration vehicles switch on their lamps, they effectively announce their presence to everything nearby. Fish, crustaceans, and gelatinous creatures often approach to investigate, sometimes in large numbers. This can lead to stunning footage, but it can also obscure the very features scientists are trying to observe. A perfectly framed view of the seafloor can suddenly be filled by a drifting jellyfish, politely but firmly blocking the shot. Sensors face similar challenges. Water intake ports, designed to sample chemical properties or measure currents, can become clogged by small organisms. Delicate instruments can be fouled by biofilms or unexpected growth during longer deployments. Even short-term missions are not immune. Animals may brush against probes, altering readings or introducing noise into the data. These interactions are not acts of sabotage. They are simply the result of placing unfamiliar objects into a living environment that responds with curiosity rather than caution. Some disruptions are more subtle. Swarms of tiny organisms can scatter light, reducing visibility and complicating imaging. Larger animals passing close to sensors can create pressure or motion signals that mimic geological activity. Distinguishing between biological and environmental signals becomes a challenge, requiring careful analysis and sometimes educated guesswork. The ocean is full of movement, and not all of it is the kind scientists are looking for. There is also the issue of behavior. Deep-sea creatures often behave in ways that are poorly understood, making their interactions with equipment hard to predict. Some may follow vehicles for extended periods, repeatedly entering the field of view. Others may be startled by sound or light, darting away and stirring up sediment that clouds the water. These reactions can alter local conditions, temporarily changing the very environment being studied. From a technical perspective, designing equipment to resist biological interference is difficult. Adding protective barriers can reduce clogging, but may also interfere with measurements. Stronger lights improve visibility, but attract more attention. Every solution introduces new trade-offs. Engineers must balance the need for clear data with the reality that the deep sea is alive and responsive. For scientists, these encounters are a reminder of why exploration matters. Unexpected animals are not just obstacles. They are discoveries in their own right. Many species observed during missions are poorly documented or entirely new to science. A camera blocked by a passing creature may be frustrating in the moment, but it can also capture rare behavior or reveal previously unknown forms of life. The line between disruption and discovery is often thin. These biological surprises also slow mapping efforts in indirect ways. Time spent adjusting equipment, repeating measurements, or waiting for organisms to move on adds up. Missions have limited windows, and every interruption matters. Yet avoiding life altogether is neither possible nor desirable. The presence of organisms is part of the environment being explored. There is a human element to these moments as well. Scientists and operators often develop a sense of affection for the creatures that repeatedly appear on screen. Nicknames are given, jokes are made. These light-hearted moments do not undermine the science. They humanize it, reminding everyone involved that exploration is not just about data, but about encountering the unknown in all its forms. In the end, biological surprises are a testament to the deep ocean's vitality. They complicate missions, disrupt plans, and occasionally steal the spotlight. but they also enrich our understanding, proving that even in the most extreme environments, life thrives and interacts. Mapping the ocean means mapping a living world, and living worlds rarely cooperate with schedules. There is a persistent idea that the ocean floor is dull, flat, empty, a featureless expanse of mud stretching endlessly beneath the waves. This misconception is understandable because from the surface the ocean looks smooth and uniform, like a giant blue tablecloth pulled tight over the planet. But that calm appearance is a masterclass in misdirection. Beneath it lies one of the most dramatic landscapes on Earth, a hidden world of extremes that rivals, and in some cases surpasses, anything found on land. The ocean floor is shaped by the same geological forces that sculpt continents, but it expresses them in ways we rarely see. Towering underwater mountain ranges snake across the planet, longer than the Rockies and Andes combined. These ridges rise from the seafloor like colossal scars, marking places where the Earth's crust is slowly pulling apart. In other regions, the crust bends downward into trenches, so deep they feel less like valleys and more like wounds in the planet's surface. These features are not subtle. They are vast, powerful, and constantly evolving, hidden only by kilometers of water. Volcanoes are everywhere down there. Many are active, quietly reshaping the seafloor without the dramatic explosions we associate with eruptions on land. Lava flows spread slowly, cooling into strange formations that look more like twisted sculptures than rock. Over time, these volcanic processes build entire mountains, on some of which grow tall enough to eventually break the surface and become islands. The ocean floor is not static, it is under construction, perpetually. Then there are the plains, which sound boring until you realize how they formed. These are not empty deserts of nothingness. They are shaped by sediments drifting down from above, settling over millions of years into layers that record Earth's history, like pages in a book. Each layer holds clues about ancient climates, shifting currents, and long-gone ecosystems. What appears flat and uneventful is actually a vast archive, quietly storing information about the planet's past. The misconception persists partly because we lack everyday exposure to these features. On land, mountains demand attention. They block horizons and force roads to bend around them. Underwater, and even the largest formations remain invisible from above. A mountain thousands of meters tall can hide beneath a calm surface without leaving a ripple. This invisibility breeds indifference. If you cannot see it, it is easy to assume it is not there. Maps also play a role. Many publicly available ocean maps are low resolution, smoothing out dramatic features into gentle gradients. Trenches become shallow dips. Ridges become faint lines. The true scale and complexity are lost in translation. It is like viewing a detailed painting through frosted glass and concluding that the artist did not bother with details. Correcting this misconception matters because it shapes how we value exploration. If the ocean floor is assumed to be boring, there is little urgency to understand it. But recognizing its complexity reveals why mapping it is so important. These hidden landscapes influence ocean circulation, seismic activity, and even life distribution. They are not background scenery. They are active players in Earth's systems. There is also a storytelling problem. Space exploration has captured the imagination with images of craters, canyons, and alien terrains. The ocean floor has been less lucky, largely because it does not photograph easily. But in terms of raw drama, it more than holds its own. Imagine a canyon deeper than the Grand Canyon, a mountain range longer than any on land, and volcanoes erupting in total darkness, all happening beneath the waves. That is not boring. That is cinematic. As more detailed maps emerge, this perception is slowly changing. Each new discovery adds texture to our understanding, replacing the idea of a bland seabed with a vision of a dynamic, sculpted world. The challenge is not convincing people that these features exist. It is helping them visualize what cannot be seen directly. In the end, the ocean floor's reputation suffers from its discretion. It hides its grandeur well. But beneath the calm waves lies a landscape of extremes, waiting patiently for us to realize that boring was never the right word. Space has always had better branding. Rockets launch with dramatic flames, astronauts float gracefully, and distant planets come with names that sound like mythological deities. The ocean, by comparison, tends to show up as a blue backdrop or a vacation destination. This difference in image has had a real impact on how exploration is funded, celebrated, and prioritized. While both space and the deep sea represent frontiers of the unknown, one consistently captures the spotlight, and the other quietly waits its turn beneath the waves. Funding tells the story clearly. Space programs often receive sustained, high-profile investment, justified by national pride, technological advancement, and the promise of future expansion beyond Earth. Ocean exploration, on the other hand, is frequently funded in smaller, fragmented bursts. Projects compete for limited resources, and long-term commitments are harder to secure. This is not because the ocean is less important. It is because it is less visible, and visibility drives enthusiasm. Excitement plays a powerful role in shaping priorities. Space exploration offers clear milestones, launches, landings, firsts. These moments are easy to communicate and celebrate. Ocean exploration progresses more quietly. There are no countdowns broadcast worldwide, no flags planted on the seafloor. Discoveries happen out of sight, revealed later through reports and images that lack the immediate drama of a rocket piercing the sky. It is harder to get people excited about something they cannot watch in real time. Marketing amplifies this gap. Space agencies have mastered storytelling, turning missions into narratives of heroism and discovery. The ocean, meanwhile, struggles with perception. It is familiar, present, and therefore easy to overlook. The idea that the greatest unknown on Earth lies just beneath our feet does not sound as exotic as worlds orbiting distant stars, even though it arguably should. There is also a psychological element. Space feels like a challenge to conquer. The ocean feels like something we already know, even when we clearly do not. This false familiarity reduces urgency. People assume the ocean's secrets can wait, that they will still be there later. Space, by contrast, feels fleeting, as if someone else might get there first. Competition fuels investment. This imbalance has practical consequences. Technologies developed for space often outpace those designed for ocean exploration, even when the latter could benefit directly from similar innovation. Engineers adapt space hardware for underwater use, rather than developing purpose-built systems at the same scale. Ocean science advances, but often by borrowing momentum from a field with more financial and cultural support. The irony is that ocean exploration has immediate relevance to life on Earth. It influences climate understanding, or resource management, and ecosystem health. Yet these connections are harder to dramatize than a distant planet. A satellite image of Mars captures imagination more easily than a complex data set about ocean circulation. One feels like adventure, the other feels like homework, even though it affects everyone. Humor helps highlight the absurdity. We celebrate finding water on Mars, while ignoring the vast, dynamic water world beneath our own planet. We send probes across millions of kilometers, but hesitate to fund missions a few kilometers down. Space gets theme music. The ocean gets a disclaimer about motion sickness. None of this is to say that space exploration is undeserving. It is a remarkable achievement and a source of inspiration. The issue is not that space receives too much attention, but that the ocean receives too little. As both frontiers matter, and both push the limits of human knowledge and technology. The difference lies in narrative, not importance. Changing priorities requires changing the story we tell. The deep ocean is not a lesser frontier. It is a parallel one, equally mysterious and arguably more relevant. Giving it the attention it deserves means acknowledging that discovery does not always require looking up. Sometimes, it requires looking down and realizing that the greatest adventure on Earth has been quietly waiting for better marketing. For most of the history of ocean exploration, progress has depended on constant human supervision. Ships hovered above, crews watched monitors, and every major decision required someone to be awake, alert, and caffeinated. This approach works, but it scales poorly. The ocean is enormous, and humans are not great at staying focused for weeks at a time while staring at slowly changing screens. Enter a new generation of technologies that promise to change the rhythm of exploration by letting machines handle more of the thinking on their own. Autonomous underwater robots are at the center of this shift. Unlike traditional vehicles that rely heavily on real-time instructions, these systems are designed to operate independently for long periods. Once deployed, they can plan routes, adjust behavior, and respond to unexpected conditions without waiting for human input. This is more than convenience. It is a fundamental change in how exploration is done. Instead of guiding every move, scientists define goals and let the machines figure out the details. Artificial intelligence makes this possible. But modern systems can analyze incoming data as it is collected, identifying patterns and anomalies on the fly. If something unusual appears, the vehicle can decide to slow down, change altitude, or take a closer look. This adaptability allows exploration to become more efficient. Interesting features are examined in greater detail, while less informative areas are passed over quickly. The result is smarter coverage, not just faster movement. One of the most promising ideas is the use of robotic swarms. Instead of sending a single, highly complex vehicle into the depths, scientists deploy many smaller units that work together. Each robot covers a portion of the area, sharing information and coordinating movements. This parallel approach dramatically increases coverage while reducing the risk associated with losing any single unit. And if one robot fails, the mission continues. The ocean becomes a space that can be explored simultaneously rather than sequentially. Autonomy also reduces dependence on surface ships. Traditional missions require a vessel to remain nearby, acting as a command center. Autonomous systems can be launched and retrieved with minimal oversight, freeing ships to support multiple operations or reducing the need for them altogether. This shift has the potential to lower costs and extend mission durations, allowing exploration to happen more frequently and in more places. Another key advancement lies in onboard decision-making. Instead of collecting everything and sorting it out later, autonomous systems can prioritize what data to store and transmit. As this selective approach conserves power and storage while focusing attention on the most valuable information. It also reduces the burden on scientists, who receive more refined data sets rather than overwhelming volumes of raw material. The machines become collaborators rather than passive tools. There is also a quiet revolution happening in how these systems learn. Artificial intelligence models improve over time, becoming better at recognizing features and anticipating conditions. Each mission contributes to the next, building a growing base of experience. Exploration becomes cumulative not just in data, but in capability. The more the ocean is explored, the better the explorers become at navigating it. Of course, autonomy introduces new challenges. Trusting machines to make decisions in unfamiliar environments requires careful testing and validation. Errors can still happen, and understanding why an autonomous system made a particular choice is not always straightforward. Transparency and reliability become as important as performance. Scientists must learn to interpret not only the data collected, but the decisions that led to its collection. Despite these challenges, the potential benefits are enormous. Autonomous technologies promise to accelerate mapping efforts by orders of magnitude, turning what once took years into months or weeks. They allow exploration to scale in ways that were previously impossible, reaching remote and difficult areas with minimal human presence. The ocean becomes less dependent on babysitting and more open to systematic, sustained study. In the end, these new technologies represent a shift in mindset. Exploration is no longer about how long humans can endure the process, but about how intelligently machines can extend our reach. The deep ocean remains challenging, but with autonomous robots and artificial intelligence leading the way, the pace of discovery is poised to quicken. The maps of the future may be drawn not by tired crews at sea, but by tireless machines quietly doing their work in the dark. For a long time, ocean exploration moved forward in careful, almost hesitant steps. Progress happened, but it felt slow, optional, and easy to postpone. That hesitation is fading. In recent years, momentum has begun to build, and for the first time, it feels like the deep ocean is shifting from a distant curiosity to an urgent priority. And this acceleration is not driven by a single discovery or invention, but by a convergence of pressures that all point in the same direction. The message is clear. We can no longer afford to treat the ocean as an afterthought. Climate change is one of the strongest forces behind this shift. The ocean plays a central role in regulating Earth's climate, absorbing heat and carbon while redistributing energy around the planet. As global temperatures rise, scientists need to understand exactly how the ocean is responding, especially in its deepest regions. Changes in deep ocean circulation, chemistry, and heat storage can influence surface conditions decades later. Ignoring these processes would be like trying to predict the weather while refusing to look at the atmosphere. Extreme events have sharpened this urgency. Marine heat waves, shifting currents, and altered ecosystems are no longer abstract predictions. They are measurable realities. To understand their causes and consequences, researchers must look beyond surface observations and into the deep ocean, where long-term changes quietly accumulate. Mapping and monitoring these regions is no longer optional background research. It is essential for understanding the planet's future. Resource needs add another layer of pressure. The ocean contains materials and energy sources that are increasingly discussed as societies search for alternatives to traditional resources. Before any decisions can be made responsibly, we need to know what is actually down there, where it is, and how it is connected to surrounding environments. Exploration provides the baseline knowledge required to evaluate risks and benefits. Without it, her decisions are made in the dark, guided by speculation rather than evidence. There is also a growing recognition that the ocean is not infinite. For much of history, it was treated as an endless reservoir, capable of absorbing impact without consequence. That illusion has been shattered. Overfishing, pollution, and habitat degradation have revealed limits we once ignored. Exploration now carries a different motivation. It is not just about discovering what exists, but about understanding what needs protection. Knowing the seafloor is a prerequisite for managing it wisely. Curiosity still plays a role, and it always will. Humans are driven to explore simply because the unknown exists. But curiosity today is sharper, more focused. It is informed by the realization that the deep ocean holds answers to questions we are already asking. How stable is the climate system? How resilient are ecosystems under stress? How does the planet respond to rapid change? These questions point downward as much as outward. Cultural attitudes are shifting as well. The narrative that exploration must involve distant worlds is being challenged. There is a growing appreciation for the idea that Earth itself remains largely unexplored. Documentaries, images, and discoveries from the deep sea are capturing public attention in new ways, reframing the ocean as a frontier rather than a backdrop. This change in perception matters because public interest influences funding, policy, and long-term commitment. Institutional priorities are evolving too. Governments and organizations increasingly recognize that ocean knowledge underpins economic stability, environmental resilience, and national planning. Exploration is becoming integrated into broader strategies rather than treated as a niche scientific pursuit. This alignment accelerates progress by embedding exploration within larger goals. Perhaps most importantly, the sense of timing has changed. There is a growing awareness that waiting comes with costs. Delaying exploration means delaying understanding, and delay reduces our ability to respond effectively to change. The ocean has been shaping Earth's systems for millions of years, but the pace of human influence is unprecedented. To keep up, knowledge must advance faster than it has in the past. All of these forces converge on a simple realization. Looking up is inspiring, but looking down is necessary. The deep ocean is no longer just a mystery waiting patiently, and it is a critical piece of the planetary puzzle, demanding attention now. Exploration is accelerating because it has to. Even after centuries of sailing, fishing, and studying the seas, the deep ocean remains largely unread. We have skimmed the cover, flipped a few pages, and confidently declared we understand the story. In reality, we are still standing at the opening paragraph, squinting at unfamiliar words, and realizing just how long the book is. What remains to be discovered beneath the waves is not a short list of details, but an entire world of unknowns that could reshape how we understand our planet. The seafloor alone holds countless features that have yet to be mapped in detail. Vast regions remain represented by rough outlines, their true shapes and structures unresolved. Hidden landscapes influence how the ocean moves, and how energy is transferred, and how geological processes unfold over time. Each unmapped area represents a gap in our understanding, a missing piece in the puzzle of how Earth functions as a system. These are not just curiosities. They are foundational elements that affect everything above them. Life in the deep ocean remains one of the greatest sources of mystery. New species are discovered regularly, and many more likely remain unseen. These organisms are not just biological oddities. They represent alternative solutions to survival, evolved under conditions unlike those on land. Studying them expands our understanding of biology itself, revealing how life adapts to extremes and how flexible living systems can be. Each discovery challenges assumptions about what is possible. The deep ocean also holds clues to Earth's history, or layers of sediment, chemical signatures, and geological formations preserve records of past events that shaped the planet. By reading these records, scientists can reconstruct ancient climates, shifts in ocean circulation, and moments of upheaval. This historical perspective is essential for understanding present changes and anticipating future ones. The past is written into the seafloor, waiting to be interpreted. there are practical implications as well. Understanding the deep ocean improves our ability to predict natural hazards, manage resources responsibly, and protect ecosystems. Knowledge reduces uncertainty, and uncertainty is costly. Decisions made without a clear picture of the environment risk unintended consequences. Exploration provides the context needed to act with foresight rather than reaction. Why does this matter now? Yet because the ocean is not separate from human life. It influences weather, food systems, and the stability of coastlines. Changes in the deep ocean eventually surface, affecting communities far from the water's edge. What happens in darkness does not stay there. It echoes upward, shaping conditions we experience every day. There is also a deeper, less tangible reason exploration matters. The unknown has always driven human progress. It challenges complacency and expands perspective. The ocean, vast and hidden, reminds us that the world is still larger than our understanding of it. In an age where information feels instant and complete, the deep sea offers humility. It shows that mystery still exists, not in distant galaxies, but on our own planet. The idea that the ocean is Earth's last great mystery is not an exaggeration. Thus, it is a recognition of scale, complexity, and depth, both literal and figurative. Unlike other frontiers, it surrounds us. It touches every continent and every life form, yet remains mostly unseen. That combination of intimacy and obscurity makes it uniquely compelling. As exploration continues, each discovery will add a sentence, a paragraph, perhaps a chapter. But the story will remain unfinished for a long time. And that is not a failure. It is an invitation. The ocean does not demand that we solve it quickly. It asks only that we keep reading, keep exploring, and keep acknowledging how much there is left to learn. We are not nearing the end of the book. We are just beginning to turn the first page.